I just gave an entire lecture, typing in as I went, um, and the recorder was not on. So I guess maybe I'll try to read through this and see if I can highlight the points and just go through it again. So we're talking about induction, and I should say, I have a cold, so please excuse me if I start coughing or have to pause for a minute. And so anyway, we can define this data type NAT, which is um, data type that has two constructors. Z, which just is a NAT. So it's a little bit like the empty list. It's a constant. It doesn't take any arguments. And S, which is a function that takes a NAT and gives back a new NAT. Now, the interpretation of Z is, Z is 0. I got that wrong. Z is 0. And the interpretation of this one is that S is the successor function, which means add 1. So this is the data type. So instances of the natural number. So NAT looks something like this. If I wrote it down as a set, it would be something like, oh, Z's in there, and S of Z is in there, and S of Z is in there. And if we're careful to make S, we could make S associate to the right, then that would be good. And then S of Z is in there. And so the way that we're going to interpret this is 0, this is 1, this is 2. Just count how many S's there are. Okay? So if we want to define addition so that it behaves like the addition that we all know and love on NATs, here it is. We're defining it by recursion on the structure of the first argument. So what is the type of add, if I want to put that in? It's a function that takes a NAT and takes another NAT and returns a NAT. And so here's the first NAT, and here's the second NAT, and here's what gets returned. So if I add 0 plus k, that's equal to k. And if I add the successor of j to k, it's just the successor of adding j to k. So that's a definition for add. Now, one thing, if this is correct, one thing we'd like to prove is that we can look at the definition and we see right away that that Z on the left, Z plus K is equal to K. But what we'd also like is that for every J, J plus Z is equal to J. So 0 works on the left or the right side of addition. And so I'm going to use equals equals in these properties. So what's the property? Now, this is sometimes confusing, but basically you just strip off the first quantifier. This formula to the right of the quantifier, this formula here is a property of J. And so I could say P of J is equal to add J to Z is equal to J. So now if I have that definition, this just becomes this. For all J, which is a NAT, P of J holds. So now we might start by thinking, okay, well, we'll just prove this thing. It must be easy. It's dead trivial. So we say, okay, one way we could proceed is by considering how the first argument is constructed, or how J actually is constructed. You can see J is the first argument to add here, but how J is constructed. Well, J has to be either 0 or it has to be an S of K. And if it's 0, P of Z just says add Z equals Z. But that's true because if I replace K up here by Z, then it's true that add 0 to 0 is equal to 0 by the definition of addition. Okay, now what about the second case where we want to check it for S of K, for some K? So then we replace carefully all the J's in the property. So here's our property. We replace all the J's by S of K's. And so we get add S of K to Z is equal to S of K. So that's fine. That's what we want. We want to say if we add 0 on the right to S of K, it's equal to S of K. So if we start on the left side and we use the definition of addition, we get that add S of J to Z is equal to the successor of add J to Z. And we'd like to be able to claim that, oh, this is equal to J, but we don't have any way to do it. We have no way to proceed. We have an S and we have something about add JZ. We can't simplify that by any rule that we have because now we could try cases again. Like you could really start going down the rabbit hole, try cases on J, and then you'll get stuck at this point again. And then you could try cases again on whatever you chose after J, J1, J2, J3, and you'll see you'll get stuck kind of in a loop unfolding and saying, oh, well, J has to be either 0 or a successor. And so, but you could also be a little clever and discover at this case point, this looks just like what we're already trying to prove. So we failed. This proof fails. We cannot prove this. Now, we do have an induction principle on NATs. And so here's the induction principle for NATs. And I can put the types in here to make it more complete, I guess. It makes it a little harder to read, maybe, but it says, okay, if you can show P holds for Z, and if you choose an arbitrary K, which is a natural number, and you assume that P holds for K, using that, if you can show P of S of K, then these two things together have shown that for every J of type NAT, the property holds for J. Now, what I did is I said, well, look, Z is just 0, and S of K is just K plus 1. And if you look at this, you might recognize the ordinary principle of mathematical induction, which you saw in, 2300. So, but this looks a little complicated. It's like a big formula. So how do we apply the principle? How do we apply the principle? Well, if we want to show this, if we want to show for every J, P of J is true, and I can add the types in here. Show two things. Show the base case, show that P of Z is true, and the induction step. And to do the induction step, what you do is you assume P of K is true. In other words, you're trying to prove this. And so what do? First, you choose an arbitrary K. And then how do you prove it implies? You assume P of K and show P of K plus 1. So what do? We, I should say, assume P of K is true for an arbitrary K in NAT and show P of S of K. And note that what we call P of K, the assumption P of K, the induction hypothesis. That is what we're assuming. So now let's go back to our theorem, and we want to show that for every J that's in that, add J 0. So j plus 0 should be j. And the proof is by induction on j this time. And the property P of j is add jz equals j. So the base case is show P of z, i.e. that add z to z is equal to z. But again, that's true by definition of add. That's just plug in. Could look at your definition of add up here, and you could just plug in k to be 0. And so you have add z equals z. So what about the induction step? So we assume P of j for arbitrary j, and we have to show P of s of j. So the induction hypothesis, P of j, is that if we add j to z, we get back j. And we must show that, oops, that should be capital, P of s of j, i.e. that if you add s of j to z, you get back s of j. So let's use the definition. Add s of j to z is, and this is by definition of add, equal to s of add jz. So to add a successor to something, you take the successor of the result of adding the thing being successorized, j, to the second thing, z. So this was from the definition of add. But now look, I know, and from my induction hypothesis, I know that add jz is equal to j. So I know that this add jz is equal to s of j, and that's what we had to show. We had to show that this was equal to this, and so we're done. Okay, so that's kind of a short lecture on induction on gnats. I'm going to do another one now with induction on, if I can figure out how to get out of Screencastify. Come on. Oh, God, come on.